Okay. Hello, class, and others who may be just tuning in. I want to go over the test with you all. In addition to that, I want to speak about the effect size, which would be Cohen's D, and also variance explained, R squared. And when to do this, you're going to need Microsoft Excel, and you should download JASP, JASP. You can find at jasp.org. Okay, so we're going to use these programs so that we can run the t-test, which is an inferential statistic application. We'll be able to, when we run a t-test, take a sample of scores and compare that sample to a hypothesized population mean or like a standard mean. And then we'll be able to see if the treatment that was applied to the sample or the condition of that sample does in effect lend that sample to be a part of another population mean that we can think of, right? Or if that sample is coming from a population mean that is similar or the same as the standard that we're comparing it to. Right, so this is where we get into our 95% confidence interval, right? And we're looking for a t-score that either lies within the 95% confidence interval or lie without. Okay, also, when we look at effect size, we know that we consider the sample size when we're running our t-test and our z-test. And sample size does have an effect on the t-score. As sample size increases, t is going to increase. We know that sample size, increasing sample size lends to a t distribution that's more like a normal distribution. We also understand that as sample size increases, you're increasing more of the population. So you're in essence reducing error. So what can happen is you can run a t-test with a sample size that is large enough to give you a significant t, even if you have a very small treatment effect. All right, so when we look at Cohen's D, I'm going to just share the screen so you can take a look at the formula. When you look at Cohen's D here, we actually remove the n. If you remember with our t formula, we would divide this sample standard deviation. This would be divided by t. All right. I'm sorry, not by t, by the sample size, which would be n or lowercase n. All right, and this would give us our estimated standard error of the mean. All right, so then we have, this is where we get t from. All right, when we're computing Cohen's D, we're looking just at the difference between the two means, and we're looking at standard deviation. All right, so Cohen's D 0.2 is a small effect, 0.5 the medium effect, and 0.8 is a large effect. We're also going to look at R squared, which is the percentage of variance explained. This formula is pretty straightforward. T squared is going to be divided by t squared plus degrees of freedom. We know degrees of freedom is sample size minus 1. I'm also going to take us through on a bit of a journey through like a definitional formula of R squared, where I'm going to show you how we're able to pull the effect size and then compute the sum of squares without the treatment effect. So we can consider a treatment effect just the difference between the two means. We can look at, a sample mean and a population mean, and then we can, from every score, we can pull that, difference and then compute a sum of squares against the population mean. And then we'll also just run the scores, the sample scores as we have them against the population mean as a deviation, right? A different type of deviation, because now we're not using the sample mean to compute the deviation. We'll be using the population mean against the sample scores. So then we'll end up with two sum of squares, a little bit different than what we're used to when we consider sum of squares, but these are two types of sum of squares. And then from there, we'll be able to extract what we consider to be the percentage that is explained by the treatment effect. So we get there when we get there. All right, so let's just take our time, and we're going to start with just running our t-test. Okay, so let's just look at this example. And let me hit this so you're not confused. So we have, infants, even newborns, babies, they're going to, sorry, even newborns, they're going to gaze longer at the more attractive face during a 20-second interval. If you have the graviter text, you can take a look at page, where do we start this example? Page 276 and look forward, and you'll just see some of the pointers and some of the data you'll see as well. So we have 9 infants that are going to be participating in this study. So consider that you have a 20-second interval for the newborn to look at 1 or 2 faces. So how many seconds are spent looking at the faces that have already been predetermined through like the focus groups as being more attractive? All right, so, and we are going to look at a score of 10 as our null hypothesis, meaning that they're looking at equally at both scores, at both scores. You're looking at both faces equally, so you're spending equal time. So maybe let's just say if you had 2 babies in this study, one baby spends 11 seconds looking at the more attractive face, and the other baby spends 9 seconds, or you have a mean of 10. It's pretty much saying that, babies, they look at either face and there really isn't a difference whether or not one of the faces are attractive or not. All right, so that would be sort of our null hypothesis. Okay, so our null hypothesis. We're going to say that the population mean that this sample comes from is equal to 10. This should be a colon. And then we have our alternative hypothesis. And I could have written this up earlier, but I kind of want you all to kind of take the steps with me. Walk with me here. I'm going to say it's not equal to. I wonder if there's a symbol for that. Not equal. Probably not. Or maybe. Yeah, yep, that's here. Okay, so we have our null and our alternative hypothesis. We're going to set alpha at 0.05, so we're using a 95% confidence interval. I know I could find alpha. Alpha equal to 0.05. All right, so now we're set, right? So we set our criterion. Okay, we can look even further now that we know our sample size, we know degrees of freedom is going to be equal to 8. So we can find the critical value for T. So you can just go into if you have a textbook, or you can find this online, I just look up the T distribution. For those that are working out of the gravity text, you can turn to page 651. Proportion in 2 tails combined 0.05, degrees of freedom 8. We have a critical T value of 2.306. So T critical is going to equal 2.306. So we need a t-value that's greater than 2.306 in order to reject the null hypothesis. Sorry, 0.05. Our critical t at 0.05 is equal to 2.306. All right, so we're about ready to go. And again, we're going to look at our Cohen's d after we after we're finished. Okay, so let's see. I have the data up. I call it the t-test example babies. Okay, we can quickly, just save this data. 8, 10, 12, 12, 13, 13, 15, 17, 17. This is how long the babies are gazing at the more attractive face during a 20-second interval. Okay, so this is your data. When we place this data into JASP, we'll be able to pull our descriptives, the mean, median, and mode. But we understand that, right? In Excel, we can also just quickly look at the average if we wanted to. So let's just, for the sake of, all right, so that's going to be A2 colon A10. All right, so we know already we have a treatment effect that's going to, or an absolute treatment effect that's going to be in the range of 3. We know with Cohen's d, you're going to also divide, by the standard deviation. Excuse me, but we know we're looking at a treatment effect of 3, especially when we get into the R squared, that formula. Or should I say that more definitional formula, taking that apart. All right, so let me just delete this so it doesn't mess up the data that we're going to transfer. So remember, your data should be saved in Excel in an ODS file because JASP reads the ODS file. Okay, so make sure that you have that done. Okay, I'm going to just save this again just to be sure. All right, so now we're going to open recent files. Is it there? No. Okay. I'll browse. It's probably in the, there we go. T-test example babies. All right, so it's importing data from the ODS. All right, so here's our data that we were expected: 8, 10, 12, 12, 13, 13, 15, 17. Let's run our descriptives. We always want to run our descriptives and make sure that we have the descriptives that we want to look at. We want to look at our mean, median, and mode. Maybe in the next video, we'll discuss the skewness. We have variance, standard deviation, and we have the range. Okay, so we have a range of 9. Standard deviation is going to be 3. Median is 13, mode is 12, and the mean is 13. Okay, so small number of scores, but we have our measures of central tendency are pretty much in line with each other. All right, let's run the one sample t-test. Okay, our alternative hypothesis. Okay, so we have the student t. Going to add effect size. And the alternative hypothesis is that we're not equal to the test value. What is our test value? Our test value is 10. Remember, that's our hypothesized population mean. Okay, we have this bug, computed effect sizes, ignore the test value. So maybe the Cohen's D might be a little off, but let's see when we get there. Okay, so what do we have here? We have the one sample T test. We have a T value of 3. All right, we can look back at our notes that we have. We have a critical T of 2.306. And we now have a T of 3. So we understand that that T is going to be significant. It's going to lie outside the 95% confidence interval. Okay. Probabilities here is set. You know, the probability of finding such a T is going to be 17,000. So again, it's outside of 0.05, right? The probability is less than 5%. Right, so we have a significance, we found significance. So the attractive faces do have that effect on the newborns. All right, so if we would consider Cohen's D, we want to look into effect size, just to make sure that this effect size of 4.33 is what we would have found if we ran the formula. Okay, so we have a standard deviation of 3. We have a sample, the difference between our sample mean 13, population mean 10. So we can already see that it's computing, that bug is in effect. We would have 13 minus 10 divided by 3, and that would give us 1. So Cohen's D is actually equal to 1, which is a large effect. Okay, it's greater than 0.08. The R squared, the percentage of variance explained. Let's run that ourselves. We do have a T value of 3. So we're looking at 3 divided by 3 plus degrees of freedom, or 3 divided by 11. Okay, and we can compute this pretty fast. Well, first we need to take T and make it T squared, right? So that's actually 9 divided by 9 plus 8. So that's 9 divided by 17. And that gives us 52% of, or 53 is 52.9% of the variance is explained by the treatment effect. Or this treatment meaning the attractive faces is actually causing leading to these changes that we're seeing. All right, so and again, that's a large effect. We can see 52.9% compared to 0.25. Okay, I also wanted to give you all a view of what I consider the more definitional formula of the percentage of variance explained. So you can see just where the numbers are coming from exactly. All right, so I stated that you would take the sample scores and we would subtract, from each score, we're going to subtract the population mean, or the hypothesized population mean. Then we're going to take each score, remove the treatment effect, and then subtract that hypothesized population mean. So we're taking, these are the same scores. Remember, we're not going to apply the constant yet. So we're going to take every score, 8, 10, 12, 12, 13, 13, 15, 17, 17. And we're going to compute a sum of squares, but not using the sample mean of 13. We're going to be using 10, the population mean. All right, so from each score, you subtract 10. And so from 8, you would have -2. From 10, you'd have 0. From 12, you would have 2, right? We're subtracting 10. And then we're going to square. All right, we're going to square the deviations from the hypothesized population mean. Right, this is going to give us a sum of squares of 153. I wrote in the note, be mindful that this sum of squares is computed with the hypothesized population mean of 10, not the sample mean of 13. Otherwise, our sample has a sum of squares of 72. If we were to subtract the sample mean from all of these scores, we would find ourselves with a sum of squares of 72, which is actually going to be the sum of squares when you remove the treatment effect from all of these scores. So removing the treatment effect of 3, remember we have population mean 10, hypothesized population mean 10, sample mean 13. So let's subtract that treatment effect from each score, then compute the sum of squares with this treatment effect removed. Okay, so you're going to subtract 3 from every score, and then from that, you have a score that you would then subtract the deviation of the population mean, the hypothesized population mean of 10. Okay, so how does that work? Just to be clear or help you out, you can see 8 minus 3 is 5. 5 minus 10 is negative 5. Okay, 10 minus 3 is going to be 7. 7 minus 10 would be negative 3. 12 minus 3 is going to equal 9. 9 minus 10 would be negative 1. All right, and so on and so forth, moving down. Maybe I should just fill this out so there's no confusion. Okay, and of course, all of these deviations from the population mean are going to be squared. And then we have 72. So now what are we looking at? We're looking at the sum of squares, right, which would be our total, right, which would be 153. We're considering them all the scores just in their totality with the treatment included. And then we're going to, we're going to subtract the population mean from those. That gives us 153. And then we remove the treatment effect, all right, which is that difference of 3. And now we have 72. So if we subtract 153, which is like our total on variability accounted for, with the variability accounted with the treatment effect removed, it gives us 81. Okay, so 81 is going to sort of represent, right, the variability of the treatment, or the variability accounted for with the treatment. That's 81. 81 divided by the total 153 gives us 52.94% of the variability accounted for by the treatment. Okay, so that's long. Okay, so right, so of course you would prefer to run the formula with the t squared. And we'll also in the future, we'll be looking at some other programs that are going to give you that variance explained by the treatment, or R squared. Be able to give you that in the actual program. I've still been looking at JASP to figure it out. Maybe somebody who's a more advanced JASP user would say, oh, this is easy. But as of right now, we have some issues with our effect sizes on JASP. As you can see, even running Cohen's D, and we got 4.33, which is not, the Cohen's D that we computed. We had a Cohen's D of 1, but they already stated that they had a bug, right? But it's just good that you understand the discussion of treatment effect, in addition to your computed t-score. All right, so here we, again, just to wrap it up, we'll be able to say that attractive faces influence newborns to gaze longer. Okay, and if anything else you'd want to add, I mean, you probably could just speak to just talking statistics, right? We always want to have a lay person's statement at the end of our test. But right, you can just say that if you want to just talk about your hypotheses, right, that you're going to reject the null hypothesis. You could say that this sample comes from a different population than the standard population that we're comparing it to, which we would say is just a population of where the newborns are not affected by the faces, or where there's just no treatment at play, right? We can say that once you add this treatment, right, there's now you're working with a different population, right? And you can see that because where the newborns are placed on the T distribution, they're placed outside the 95% confidence interval. So the only way we could say this treatment didn't have effect would be if we had a type 1 error, which would be equal to 5%. No, usually we look at that 5% as just chance. All right, so hopefully this has been helpful and instructive. Again, we'll come back with more videos like this where you can take a look at the computer programs. And this is great because it's a program that's free for you all to use. And for my classmates, if you have any questions, again, you know where to share those questions. So thank you.